As Jim was just saying, right, Elliot Rappaport, and presently on the faculty at Maine Maritime Academy, where I just got through explaining. I teach, like most of the people on the faculty, I teach a little bit of everything. Navigation, both celestial and traditional navigation and modern navigation, meteorology, a little bit of boat building, and rules of the road, just sort of all the on the deck side of things, right? All the skills that you need to take a ship to sea as an officer. I spent this slide. I like to put this slide up because it just sort of gives an idea of just a sampling. If you say you're a professional mariner, there's an incredible range of vessels that you can find yourselves on at sea. And I spent most of my career at sea in traditional sailing ships and oceanographic research vessels, sometimes at the same time. This is the Corwith Kramer, which is a brigantine, a steel brigantine, relatively modern vessel, but built by and for the Sea Education Association down Woods Hole. And they run a series of sailing ships as oceanographic research vessels. But yeah, there's just the tug and barge industry, right? Container ships, and I always like to throw this number in down at the bottom of this first slide. What do you think that number is getting at? Like, what is 11 billion tons? 11 billion tons of what? What do we think?
Stuffed animals.
Okay, so 11 billion tons, right? That's the average annual tonnage of shipping, okay, at sea on the world's ocean, okay? And I just like to throw that out because we tend to think of shipping, particularly when you're standing in a room like this, right? Shipping and seafaring is a historic and very, very historic and traditional occupation, and it is. But there are more ships and more seafarers and more cargo at sea now by orders of magnitude than in any other time in history. So this is a screen capture. Oh no. There we go. This is that was a short slideshow. Okay, so this is a screen capture from something called marinetraffic.com, and these are signals from ships. Ships, for the most part, commercial ships all now carry a device called an AIS, which is like an identification transponder that enables you can identify them, and both their type and their location. So, this was taken a few weeks ago, but pretty much on any given day, you can log on to this site and, maybe find your favorite ship or just view the world's oceans. And it really looks like you can walk from one vessel to the other. So there's an astonishing number of ships at sea now, and people out there earning their living as mariners. So it turns out, right, I wrote this book, Reading the Glass, and, it's a little bit about the book itself. First of all, this is a book about weather. I'm not a meteorologist, or basically, at the 100 level, right? I'm an end user of weather as a mariner. It's, good idea if you're a mariner to understand weather and to understand what the people who really understand it, the tools, the terminology they have for communicating, and the tools you have at sea for learning about the weather and working with the weather. But scientifically, I'm not trained as a meteorologist. I guess I'm trained as a mariner, and a history degree from college a long time ago. And I didn't really think of myself as an author either, although here I am with this book. But how this developed is, I have a long-standing interest in weather. But the maritime environment is one of the sort of ultimate on-the-job training occupations, and I think it's really all I've ever done for a living. So I can't really speak that well to other occupations. But you learn a tremendous amount of about operating ships while you're actually on the job, right? You can go to a maritime academy if you want and kind of get started, but most of what you learn happens at sea, and you learn it by doing, and you learn it through just a long series of sort of excellent explanations by people who know more about it than you. And so mariners are incredible. They're sort of multi-skilled individuals, right? They're all sort of polymaths, and they're all, for the most part, very good at teaching and explaining. That's kind of how important training is as part of the environment. And I'm also pretty, I like to read. I've always enjoyed books, and I've always really enjoyed books that tell a story about some, a complicated topic, okay? And so, science itself, right, is really, science itself is continuously challenged by, you not only need to understand science, but you need to understand how to tell the story of science so that more people can understand it. Communication is one of the biggest challenges that scientists face. So, very interested in trying to tell stories about, interesting stuff. In fact, one of the one of the editors that I talked to about the book, he said, yeah, I just read this great book. It was 70,000 words, and it was all about ladders. And he said, like, who knew that you could write, a full-length book about ladders? But it was amazing. And I was like, yeah, that was kind of, I had those sorts of things in mind when I set out to try to put this thing together. But it really began with a series of, chapters and things like that I'd really just written to share with students and trainees, in various ships and teaching situations I'd found myself in. So anyway, what is weather? This is the best summation of what weather actually is. Unfortunately, I was by a guy named Finn Perry, who's a tremendously accomplished cruising sailor, also a writer. You may have read some of his stuff in Wooden Boat magazine, and a builder by trade, just tremendously talented guy. As I saw, right, weather is the first law of thermodynamics. That's the law that says energy can't be created or destroyed. Influenced by the Coriolis effect. And the Coriolis effect is that sort of rotational aspect that things in the atmosphere take on because the Earth is a rotating frame of reference. So these two things together, first law of thermodynamics and the Coriolis effect, that was like the most elegant summation of weather I'd ever heard. Unfortunately, I heard it after I'd written the book, so didn't make it in the book, but I like to put it out there. I like to tip my hat that it was really perfect. So today what I want to talk about is kind of a quick tour of weather fundamentals, right? I teach meteorology at Maine Maritime Academy. It takes 3 months, but I think you guys are all smarter than the average Maine Maritime Academy student, I'm thinking, so we'll get this done in a few minutes. I'd like to talk a little bit about how, the global wind patterns, right, have influenced the migration of people around the globe, and quite fitting, right, that we should, have the Virginia right outside the door, right, living piece of how that took place. And then also, we're all right now, justifiably concerned with, how the changing climate is having an impact on sort of all parts of our lives, right? And, I frequently get asked about, what does climate change mean in terms of marine navigation? And again, I get to the disclaimer of not a scientist, right? Certainly not a climatologist, but can speak a little bit to some of what the potential impacts of that will be and some of what we might be seeing already. So, as our whirlwind tour of the atmosphere is about to begin. So the atmosphere, depending on how you measure, is roughly 100 miles thick, more or less. It's made mostly of nitrogen. There's some oxygen there, and also quite a bit of water vapor, which winds up being pretty important. But actually, weather really happens for the most part in a very, very thin layer of the atmosphere called the troposphere, which is the layer that's closest to the Earth's surface, about 90% of the atmosphere by mass. Okay, so most of the atoms, molecules, of the atmosphere are all within about 10 miles of the surface. So all the pretty much all the air that we breathe and all the water vapor is down very, very close to the surface. Okay, so we think of as weather as very three-dimensional, but it's happening in a very, very thin layer, kind of like the skin of an onion, or another very apt description, which I didn't come up with, right? But Sally Ride, is an astronaut who flew on the space shuttle in the 1980s. She was just taken by how thin the atmosphere looked. Looking back at the Earth, she compared it to the fuzz on a tennis ball, I think was the simile that she used. Okay, so weather is just the mixing of the atmosphere as different parts of the atmosphere receive energy from the sun, and they receive it at different rates, having mostly to do, and kind of intuitively we have a relationship with that. We understand that, the northern regions, right, the higher latitudes, northern and southern regions, polar regions are colder, the tropics are warmer, and then locally, the atmosphere exists at different temperatures. And what happens, okay, on any scale, when you have colder air is more dense and tends to sink towards the surface under the influence of gravity. And as it does so, it displaces warm air. So warm air doesn't really rise so much as it's pushed back up by cold air sinking around it. But you can think of that however you like. But where cold air is sinking at the surface, that tends to elevate. If you were able to measure the pressure of the atmosphere, if you had a barometer, measure the pressure of the atmosphere, it tends to be higher where air is sinking, and it tends to be lower where air is rising. Okay. Another thing that's important to keep in mind is that as air gets lifted, it cools off, and as all air has a significant amount of water vapor, which is just the gaseous form of water. You can't see it; it's invisible. But when you lift it up and cool it off, it turns into clouds, right, which are droplets of liquid water and or ice crystals. Okay, so that's condensation, or if you're a chemist, right, can turn into ice. That's actually something called deposition. But same thing, it's water vapor turning into liquid water, water droplets, and ice. That's clouds, okay? So another important part of the weather. Air gets lifted, it cools off, and makes clouds. So this is just another diagram of the same process, okay? We have, an area of high pressure with colder air sinking, an area of lower pressure where warmer air is being pushed aloft or rising, okay? In general, we tend to think about, when we think of wind is just the flow of air from areas of higher pressure towards lower pressure. So, nature hates a vacuum, right? So the pressure is going to try to equalize. So if we have an area of high pressure with, cooler air sinking in an area of low pressure with warmer air rising, at the surface we're going to get wind flowing from high towards low. What we don't think about really in the day-to-day is there's actually quite a bit of wind up high, kind of up where airplanes fly, roughly at about that altitude. That's air that's influenced by this flow at the surface, but it's basically flowing from place to place to replace air that's been, if you have air that's sinking, right, it can't sink forever. Wind needs to flow in from somewhere to fill the space that's been left, if you will. So most, wind is really, when we see wind at the surface, it's really part of a circulatory pattern that's going on. And I've got a better slide of that in a second. But the main thing that this slide is meant to show is this phenomenon called the Coriolis effect, which is that because the Earth is a rotating frame of reference, and we could do a whole lecture on the Coriolis effect, but that's much less interesting. But for us, right, to understand that wind tends to have a rotational pattern around high and low pressure systems, and that's because the fact that the Earth is a rotating frame of reference makes wind as it flows tend to be deflected. And I think for right now, just sort of for tonight, understand that around the low pressure system in the northern hemisphere, low pressure systems has what's called a cyclonic flow, which means that around a low pressure system, the general direction of wind at the surface is counterclockwise in the northern hemisphere. This doesn't have anything to do with the way your toilet flushes, okay? But it's just a rotation that's imparted by the fact that the Earth is rotating. We're looking at the atmosphere in a rotating frame of reference. And a high pressure system, or a place where air is sinking to the surface, the general rotation of wind in a high pressure system or a place where air is sinking is generally clockwise, again, in the northern hemisphere. Okay, so another step towards weather basics, right? Like I said in the previous slide, right, we see, wind is created by the flow of air between high and low pressure, okay? And when we look at sort of a standard, one of our tools for interpreting the weather is this thing called a weather map. And this is a weather map that's not today's, unfortunately it's yesterday's, okay? I downloaded this from the NOAA's Ocean Prediction Center. There's a bunch of stuff on here, but what I'd like you to focus on are just all these funny wavy lines, okay? And these are called isobars, which are lines of equal atmospheric pressure. So just like a topographical map, okay? If you were going out for a hike, where would you expect to find the steepest terrain?
Right there.
Yeah, right there, right where the lines were spaced the most closely, right? So in a weather map, instead of looking at lines on a hiking map, you're looking at lines of equal elevation. In a weather map, these are lines of equal pressure, okay? So, and the so-called gradient, right, the change in pressure with area determines the strength of the wind. So you can find, right, this steepest hill on our map here, and what do we see? That's a low pressure system, okay? So we've got counterclockwise flows. You can also see they've labeled it as a gale, okay? So that's a wind between 35 and 45 knots. So a significant weather feature, okay, out at sea. You can also see, like right over in New England, all this fantastic weather we've had this week, we've just kind of got this big stable mass of high pressure sitting right over us, right? And we've all, had a great run of days. You kind of see this on this map. We'll come back to this. We can see there's actually some stuff going on down here in the tropics that we'll talk about in a few minutes. So, but for right now, right, the steeper the gradient, steeper the change in pressure, the more wind that you get. Okay, so let's take a deep breath, okay, and take a look at this diagram, okay, and what we are looking at here is a sort of a orthographic three-dimensional drawing of how the atmosphere circulates, and we're looking at we're looking at one hemisphere, okay? So on the right-hand side of this diagram, we're looking at the equator, okay? And I've just, sort of labeled it roughly. If you're at the equator, you're making your way north. Okay, here we have the equator, the city of Guayaquil in Ecuador, right, which actually means equator in Spanish, right, sits right about at the equator. And then here we have the North Pole, okay, 90 degrees latitude. And in the tropics, the atmosphere is warmest, okay, so we have the warmest air in the tropics, the coldest air in the poles. And just in a very idealized sense, the way the atmosphere behaves is that in the tropics we've got a lot of warm air that's steadily being lifted. It's the warmest, wettest, least dense air on the surface of the Earth. So it's being sort of lifted up, and gradually, if we get up high, it's being lifted up out of the tropics and sort of making its way gradually back towards the poles, okay? And this creates this sort of model that meteorologists or earth scientists talk about as being like a 3-cell system of atmospheric circulation. But the important parts of it to think about is we've got a lot of air that's being lifted up out of the tropics. We have air that's flowing in at the surface to replace it. And then it gets lifted up out of the tropics and begins to flow towards the poles. And as it does, it starts to cool off, okay? And as it cools off, it gets denser and it starts to sink towards the surface. Right around, about a third of the way to the pole, right around areas that we think about climatically, we tend to think about as areas of being, relatively stable climate, right? So anybody been to Bermuda? Pretty nice there a lot of the time. You've been to San Diego? Okay, a lot different than Bermuda, okay, but it's also an area, it's right around this latitude. It's a part of the planet where there's a lot of air that's been lifted up out of the tropics and sort of cooling and sinking and making its way back towards the surface. Anybody been to New England? Anybody been to Maine? Okay, so what's the weather like here? Right, call me in an hour, right? So the weather here is very changeable, okay, and the weather in we'll say the middle latitudes is characterized by the fact as we get, air that makes its way back to the surface, it's still relatively warm, and as it spreads out, it tends to at some point meet very cold air from the poles, right? So our weather in the in our latitudes, right, day by day it's very changeable, but in general it's characterized by the mixing between sort of warmer air from the lower latitudes and cold polar air. And at the surface we call that the polar front. It's just kind of like a general term, but it's also characterized by we get mixing at the surface, and then this boundary between cold polar air and sort of warmer air from the middle latitudes is characterized kind of up high, again kind of at jet plane level, is characterized by this river of wind. It's generally flowing from west to east. It kind of zigzags around, and that's the jet stream, or it's a jet stream, okay? It's the strongest strongest current of air in the upper atmosphere. It's the jet stream, or more precisely the polar jet stream, right? And that's a current of air that sort of runs along this boundary between the kind of warmer air from the middle latitudes and the colder air from the poles. And it's down to the fact that in general, right, we're up here in the upper part of the troposphere, and generally the air is flowing, from the tropics towards the poles, but it's getting pulled to the right by the Coriolis effect. So it concentrates in these very strong westerly bands of air, okay? So that's what drives the jet stream, or jet streams. There's several of them in the atmosphere, and they're like rivers. They're identifiably fairly continuous, and the weather at the surface, particularly where we are, tends to be much more changeable. So sort of more on that later. This is, you find this type of diagram in, pretty much any earth science textbook, various versions of it, but I think this is my favorite just in terms of the way that they've drawn it. So you can generalize. So we take a look at this diagram, right? And what this next diagram here does is we're just looking at the world in cross section, and we can see the same system we were just looking at. We've got wind being lifted up out of the tropics. Okay, here's Bermuda, where wind is sinking back to the surface, and then here's the polar front. Okay, so here's where we are, just about halfway to the pole, and you can see we get very active mixing between sort of warmer air making its way up from the middle latitudes and cold polar air sort of making its way to the south. So this sort of 3-cell system that we were just looking at, you can identify it more or less in every hemisphere, okay? And heavily influenced by local conditions and topography and things like that. What this does is it sets up a pattern of global winds, again, that you can sort of in cartoon fashion, you can identify globally, right, depending on latitudes, right? Has anybody been lucky enough to spend any time in the tropics? Buddy, where's the wind come from generally there? What's the weather like? Warm all the time? Yeah, pretty reliably from the east, right? Nearly all the time. If you get wind, it's out of the east, okay? And those are the trade winds, right? And those are created by the fact that you get air that's being lifted up out of the tropics, air is flowing in to replace it, and it's getting deflected by the Coriolis effect. So on either side of the, either side of the tropics, right, we get air flowing towards the tropics and being bent around by the Coriolis effect, so that instead of being just north to south, when you get into the tropics, it's actually mostly an easterly wind. So those are the trade winds, and they're very, very reliable because the tropics are always absorbing thermal energy. They're always absorbing heat. And the sun eats the planet, right? And the planet actually warms the atmosphere from below. But in any case, the tropics are warm, right? And the poles are cold. Where's the wind generally from in our latitudes, like up here? Where's the wind generally from? Southwest, northwest, right? Northeast once in a while, but generally west, right? For most of the time, it's from some part of the westerly quadrant, okay? And again, it's not as consistent as the trade winds, right? You can't bet on, the wind being out of the trade winds, right? Blow from the same direction for days after days after days. But up here, right, in our latitudes, the winds are generally out of the west, okay, with some variability, but the general trend is out of the west. So, right, if you're in the tropics, right, this is life in the tropics, generally easterly trade winds. You got a lot of mileage out of your square sails, right, which are sails that are designed for sailing downwind. The weather is sort of characterized by a lot of convection. That's just a sort of upward circulation of air that builds big, wet, puffy clouds, okay, these cumulus clouds. But not a lot of day-to-day change in the weather. Okay, and like I say, if you've been lucky enough to be sailing in the tropics, this is probably what you've experienced. Okay, in the middle latitudes, excuse me, and by that I just sort of mean where we are. This is the same picture we were looking at earlier in the show with a little bit more information added in. Okay, so here is Maine, more or less. And what we're looking at here is, what's a product of the mixing of warm air from the southern latitudes and colder polar air, right? And as they mix, the cold polar air sinks, the warm air is pushed aloft, okay? And this whole system is set into a rotation by the Coriolis effect, okay? And this is what's called, we would just call this a low pressure system, right? And depending on how intense it was, you might call it, a gale or a storm or just a low or, a depression, right? Which is a very apt name for this kind of weather science. But again, in meteorological terms, you might call this, weather scientists sometimes call this a wave cyclone. And I think it just has to do with the fact that what's really going on here, right? You get cold air that's sinking to the surface, drifting gradually to the west, and it's lifting warm air up as it goes. And so these systems, you get generally counterclockwise rotation, and you can sort of see, like if we're here, right, when this system approaches us, we're getting westerly winds, but they're out of the southern quadrant, so relatively warm, moist southwesterly winds. And in the summertime, right, this would be rain. In the wintertime would be snow. And then, what do you observe, right? You get winds out of the southwest, maybe it gets wet and cloudy, and then, what happens? Maybe it gets, the wind gets more intense, there's a lot of activity, a lot of precipitation activity, and then, suddenly things get clearer and drier and colder, right? And that's the cold front. You get this boundary between cold air and warm air, okay? So this is sort of typical circulation. We get this happen all year long, okay? They tend to be more intense in the wintertime, but this characterizes our weather in these latitudes. But you can see that in general, this kind of a system is going to get you westerly winds, okay? Depending on where you are relative to it, you might get southwesterly winds or northwesterly winds. With one exception, right? If you're to the north of it, right? If you're up here, okay, you're going to have winds out of the easterly quadrant, okay? Southeasterly, if you're up here, maybe northeasterly winds. So we'll kind of keep that in mind as we look at a couple more examples about how mariners actually use these systems to get around. So we'll look at one more picture of global winds. We'll call this like the sailor's ocean, right? Which is just showing again just the general trend of winds. And these are trends just kind of integrated over time. And as we've seen, right, in the tropics we get very reliable easterly trade winds. And then in the middle latitudes in both hemispheres, okay, this is something that people had to discover and prove, but as we now know, right, in both hemispheres more or less, in the middle latitudes you get westerly winds. If you get far enough north, right, as we just saw, you get north of these wave cyclones, you can get easterly winds. And so if you get into very high latitudes, okay, the prevailing winds tend to be easterly. But for the most part, if you're using sail power at sea, in general, right, you're best off being kind of in the middle latitudes if you're going from west to east, and if you're going from east to west, you're better off in the tropics. Something interesting that goes on in the Indian Ocean called the monsoon system. Actually, monsoons happen all over the world, but the most powerful monsoon system is in the Indian Ocean, and that's a case. It's kind of like a very, very large-scale seasonal sea breeze. Like in the winter time, right? The Asian continent cools off, gets very, very cold, and the cold air sinks off the continent, and the winds are northerly, and then in the summertime, continent warms up, and the winds are mostly southerly. So that's another weather pattern that you can see sort of year on year that has a seasonal element to it. So let's take a look at that a little bit, and just sort of looking at the way human migration at sea, exploration, whatever you want to call it. We'll just look at a few examples from history of the many cultures that have traveled by sail power across the oceans. And we'll look in the Atlantic. We'll look at the Norse navigators, who, as far as anybody knows, were the first Europeans to get to North America. And then 400 or 500 years after them, the Southern Europeans, the Spanish and Portuguese navigators. And then we'll look again at the Indian Ocean, where there's a very, very old and ancient tradition of navigation under sail, that reaches back at least 600 or 1000 BC. Commerce and sailing ships back and forth across the Indian Ocean, sort of based on the monsoon circulation. And then in the Pacific, right, the Pacific, if you look at a map of the Pacific Ocean, right, and you look at it and it looks mostly like water, right, but if you look closely, it's all islands, right? The Pacific is just this whole constellation of little tiny islands. And those islands, by the time the Europeans got there, those islands all had established civilizations on them, right? And those people had all got there under sail, mostly in open boats, okay? And they got back and forth. So a very long established tradition of navigation under sail in the Pacific, reaching back again, as far as anybody knows, 1,000 years maybe BC. And I have an asterisk on the Polynesians because they're just sort of, they've gotten the most credit and were the largest of those civilizations, of those cultures. But there are a number of other cultures in the Pacific that had similar accomplishments in navigation and sailing. So we'll just look at a few examples. The North America, right? It's pretty much been demonstrated that the Norse navigators did get to North America. The only settlement that's actually been that's been located and proven is this place called Lanso Meadows, which is up the northern tip of Newfoundland. Fantastic place to visit if you're ever up there, seriously. And I was, figured out there was a village there for, somewhere around 100 years, okay? So they settled there, they had a working village and probably, some back and forth. So they were successful enough at being there that they were able to stay there and set up a village for, like I said, roughly 100 years. And also, they demonstrably got back to Norway at least a few times because they wrote about it, okay? So this was preserved in a written record. And then the Ingsteds were a couple. There were two Norwegian anthropologists, archaeologists who originally located this settlement, but they were using written records from the Norse sagas. So, this is not just one lucky visit, okay? They had an ongoing settlement there. Were able to get back and forth to Norway and to to Scandinavia and some of their intermittent locations or their intermediate locations, places like Greenland and Iceland. They did it in boats that look like this. Okay, this is actually a boat that's called the Draken, and she's a modern replica of a Norse, transoceanic Norse vessel. About 60, 65 feet long, open boat, very seaworthy, very wet. Okay, I have a couple of friends who did a transatlantic voyages on this vessel. Very, very wet, very fast, very seaworthy, not particularly well equipped to go to windward if there are any sailors here, right? One big square sail, so in general you're best with the wind behind you. What they were able to accomplish, or this sort of demonstrates, right, if they were able to get to North America and back again, okay, on a repeatable basis, they had a pretty good handle on the way that the weather behaved in the North Atlantic, and recognizing, again, that if you need to go west, okay, you're better off in, very high latitudes, okay, if you're in the North Atlantic, to take advantage of the sort of easterly winds that exist on the north side of these these wave cyclones or non-tropical cyclones, these large low pressure systems that sort of dominate our latitudes. Okay, and if you want to go east, okay, if you want to go home, you want to be somewhere on the south side of the circulation of this system, right? So, going west, they'd get in the high latitudes, they would make sure they stayed well to the north so they could, reap the benefit of the easterlies, and then, again, to get home again, they would make their way at least a certain distance to the south. I mean, no evidence that they ever visited Bermuda or anything like that. Who knows? Maybe they did. I guess if they had, they probably would have stayed. But they had, they had the benefit, enough knowledge of the winds to be able to use the westerlies reliably to get back across the Atlantic. And these systems, right? They're not parked. Again, like you were just noting, seasonally, depending on other things that are going on, these systems may be occurring further north to the south. So where you find the winds, right, is going to depend sort of, storm by storm, right, or system by system is going to depend on, the particular system that you're sailing in. So this is the Northern Europeans, okay. We'll say the Southern Europeans, best known are the Portuguese and Spanish navigators. And Columbus is just for an example, right? There are many people that did this or attempted it, but this is Columbus's first voyage, okay, in which he sailed south out of Spain to the Canary Islands and west in the trade winds, okay. And it was pretty well understood that you could get to the Canary Islands, but generally the winds here are northerly and then easterly. There was some challenge, right? You could sail south and west very easily, but some challenge and no small amount of apprehension about, like, how do you get back to where you came from? And the ability to do so is sort of based on this discovery, this thing they call the Volta do Mar, which means return from sea, okay? And it was, just sort of by trial, pretty much, it was discovered that if you could sail, sailing to the west, and when you're ready to sail back to the east, if you made your way to the north, okay, you would eventually get into the westerlies, okay, and those would carry you back to Europe, okay? The first version of that was actually part of the discovery of the Azores, okay, which, as far as anybody can tell, did not actually have a human population on them before the Portuguese got there. And then it was a technique that, Columbus and, several of his counterparts used for getting first to the West Indies and then back to Europe. So that was kind of a little bit of a splitting of the atom in terms of a navigational discovery, right, in terms of an understanding of the prevailing wind systems. So that was 1492, okay. Sort of the next big leap was sort of they were betting on the fact that this sort of system, right, the easterlies in the tropics and the westerlies in the higher latitudes, betting that this was mirrored in all the various oceans of the world, okay. Because they really, the Grail here, Columbus got to North America, but I think as most of us understand, right, the real money was in finding an ocean route to the East Indies, okay, India and the Spice Islands and things like that. And the first person who successfully did this was sort of a series of people. Bartholomew Diaz in 1488, so contemporary with Columbus. And then Vasco da Gama was the first one who actually made a sea voyage to India from Western Europe. But they were able to do this based on a successful bet that these prevailing wind systems, right, the trade winds, okay, easterly winds in the tropics and westerly winds in the higher latitudes were something that you could find in every ocean. We all know that now, right? You can crack open a seventh grade science textbook and see this. But you think about what a bet that must have been, okay, to do that and to pull it off successfully. Actually, to get back and forth, these are Vasco da Gama's voyages, okay, his first set of voyages. And he got to West Africa, but really the crux was to get back and forth from East Africa to India, and that really depended on a local understanding of the monsoonal season, right? If the wind was, you had, northeasterly winds, okay, in the wintertime off the Asian continent, there was no way you were getting to India. So understanding sort of what these wind patterns were and what the seasonal wind shifts were relied very heavily on knowledge gathered from this very well-established culture of navigation that existed in the Indian Ocean and had for thousands of years, right? How do you use the monsoon system seasonally to get back and forth between Africa and India and some of the islands in the eastern Indian Ocean? As I say, right, these routes were very well established, and again, 1000 BC, at least, right, and these, sailing, carrying, cargo under sail persisted in the Indian Ocean and the Arabian Sea. Really, it's kind of comparable to the persistence of cargo under sail on the east coast of the U.S., like right around the time schooners disappeared from the Maine coast, sort of World War II, right around mid-20th century. Was kind of when this tailed off. Although interestingly, this picture was taken, I didn't take this picture unfortunately, but this was taken in Madagascar in 2020, right? And just like you can kind of go out onto the coast here and see people sailing around in schooners, right? These traditional vessels and, the knowledge to operate them, right, is still operative there, okay? So, I think there's still a place kind of on my, many places I'd still like to go. This is from pictures from Wooden Boat, I believe, but but this was just a sort of remnant of thousands and thousands of these ships over the years, just carrying all sorts of cargoes and passengers and things like that back and forth between East Africa and India and Indonesia, what's now Indonesia. So we'll go back to the Pacific, okay? And as I said, right, well, this was all going on, okay? Well, the Europeans were making their way to Indonesia, the East Indies, and the West Indies, okay? The Pacific, and eventually the Pacific, right? The Europeans made their way across the Pacific right around the same time. Magellan made the first circumnavigation in the early 1500s. But at that point, the Pacific was thoroughly settled, right? The last major landmass, actually the last major landmass on Earth to be settled by humans was Aotearoa, New Zealand, right? It was the Polynesian name for New Zealand. And that was 1300 AD, roughly, okay? But a lot of the Pacific Islands, places like Samoa, was settled about 3,000 years ago, as near as anybody can tell. Tahiti was settled about 12 to 1,500 years ago. Tonga, again, very, very old. So there's populations that made their way kind of gradually out of Southeast Asia and across the islands of Oceania. What's really interesting is this is all in the tropics, right? So we think of the prevailing winds as being from the east, and yet the migration, sort of the net path of the migration, relatively easy to sail north and south. Okay, Hawaii also settled by the Polynesians, again, around the same time as New Zealand. Okay, but they're gradually making their way east across the Pacific against what on any given day, right, the wind might have been out of the east. And so this kind of indicates they had a very sophisticated understanding of what seasonal changes took place, right? You might have seasonal changes that interrupted prevailing patterns. You would also have year to year these, climate cycles, things like El Nino and things like that interrupt the sort of prevailing weather patterns. So they were able to kind of take advantage of those patterns, recognize the changes that they needed to make their way gradually east, maybe as far as South America, right? That's still in the, not yet definitively proven, but, things like looking at things like certain plant species and stuff like that are prevalent all the way across the equatorial Pacific, some of which seem to have originated in South America. So it's pretty good evidence that if the the farthest, like Rapa Nui, right, Easter Island, that's fairly close to South America, so it hasn't been disproven anyway, we'll say, that the Polynesians didn't get all the way to South America in boats that look like this, right? And actually, again, this knowledge is still very much alive. There's all these great sailing and navigational societies based in all these places now. They're building these boats and sailing them around the world with traditional sailing and navigational skills. So really tremendous. So somebody here has done that? Yeah.
No, he's going to give a talk next week.
Okay. Yeah. Well, I'll stop there. I don't want to get out on a limb. Okay. So we'll jump ahead, right? We'll look at the last sort of the end of the age of cargo under sail, okay? Kind of the late 19th century. We'll call these the clipper routes, although, clipper ship is kind of a non-term. But anyway, the final era of cargo under sail was sort of like right up into the first third of the 20th century, right? There were bulk cargoes, things like, phosphates and, salt and things like that, carried by sailing ships. And at that point, the most effective route, the most effective way to get around the world is to get down into the Southern Ocean, okay, south of South America and Africa, where there's no land here between the major continents and Antarctica. And we're in the westerly winds, and the wind blows very, very hard out of the west nearly all the time, right? The roaring 40s and the furious 50s. And so you get down there, right, and if you're, if you've got the stamina for it, you can get around there and you can sail very, very fast as long as you don't mind sailing east. Okay, getting west is more of a challenge. Nowadays, right, there's not much cargo being carried down there, but there's still very active sailing culture. Use high performance around the world, sailing competitions, races, right, and they employ the same routes, okay, sort of north-south, right, you sail south till you get down into the roaring 40s and furious 50s and away you go. And what's interesting is that a lot of the records that were set by sailing ships actually lasted well into the latter part of the 20th century, and there's actually a few that still stand, just in terms of, I can't name the specific records, but, miles, like things like miles sailed in a day and times between ports and things like that. The records, the passage-making records that were set by these ships carrying tons and tons of cargo, right, are really just in the last several decades have been displaced by, high-performance sailing yachts, high-performance, very lightweight yachts. So some tremendous accomplishments. So speaking of yachts, okay, here we are again. We're now in the satellite age, okay. So roughly 1990 to present, and this is at the point in which ships at sea were able to send transmissions and be tracked by satellite, okay. And these are the positions. These are positions of sailing vessels, just an aggregate of positions of sailing vessels, primarily yachts, right, mostly recreational vessels at this point, on sailing passages. When we look at the color coding, the blue is westbound, okay, and so you can see where the westbound routes are, pretty much confined to the tropics, okay, and then the eastbound routes are in the higher latitudes, right? So west to east, you're going to be in the higher latitudes. So the modern sailing routes really pretty much replicate the traditional clipper routes, okay, or traditional, not just the clipper routes, but just the traditional sailing routes of the original sailing cultures. Relatively easy to go north to south, okay, and you can also, by looking at this, I like this because you can kind of find, pretty clear that that's Hawaii, right, where all these tracks converge. Similarly, right, here's Bermuda, things like that, so you can kind of locate here the Canary Islands, right, a big stepping off point for people sailing west across the North Atlantic. So, just in anticipation of the question that frequently comes up is, okay, so, all these routes, right, these are all based on historic assumptions about climatology, about the atmosphere. Now we have a recognition that really over the last century, right, the atmosphere has warmed substantially. How is this affecting, or how is this likely to affect global wind patterns? And I'll go back to, retreat to saying I'm not a climatologist, so I can't give you a lot of science. But we'll start with, this is from the University of Maine, the Climate Change Institute at the University of Maine, and it presents data in a way that climate scientists really like to do, which is in terms of variability. And what this map is saying, this is a comparison between, so we have two 20-year periods roughly, 2005 to 2021. I know it's not exactly 20 years, but okay, and then the preceding 2 decades, roughly 2004 to 1979. Okay, and what these colors are this decade compared to the last decade, and how much the temperature, how much warmer things are than average, okay? So what they've done is they've taken the average temperature of the globe between 1979 and 2004, and then they've looked at the next 20 years, and wherever it's red, okay, it means the temperatures are above average, right? And the darker the red is, the higher the variance is, okay? So what you can see is, well, everything is pretty red, right? It's pretty hard to find, it's almost impossible. Blue is colder, and it's almost impossible to find blue. You can find red just about everywhere you look, and you can also look and see that the red is darkest, right? So the biggest changes have happened in the higher latitudes, okay? The poles, okay, are warming much faster than the rest of the planet. There's a couple reasons for that. You know, partly connected to the fact that as things warm, the ice melts, the ocean absorbs more heat. But at any rate, right, the poles are warmer. But anyway, the whole Earth is warmer, okay, by as much as 5 or 6 degrees Celsius. So how does this affect assumptions for navigators? So navigation, you know, particularly like when you talk about passage planning, you know, particularly under sail, but not just under sail, you know, a lot of your estimations are based on climatology, which is really just a prediction of what you'll encounter based on what's historically been encountered on a certain route at a certain time of year, okay? So a lot of that data is compiled on something called a pilot chart. Probably some of you are familiar with these, but it's just, there's a ton of information on here, I'm sorry, but what this really is, right, it's a map of the North Atlantic, and these are month by month. So this is September, okay, so this is this month, okay, and this is like a whole, you know, period of September, sort of average climatic conditions for the month of September. So you can look at a pilot chart and you can determine, you know, on average, right, you know, what is the sea temperature is going to be, you know, what is the likelihood that I'm going to encounter winds from a certain direction, how many tropical cyclones have there been, things like that. So these are all built from, you know, like many years of compiled data from many ships, actually starting with this character named Matthew Fontaine Maury, who was one of the founders of the U.S. Naval Observatory in the early first half of the 19th century. And he just collected, you know, reams and reams of weather observations over history from ships and just developed this idea of the product. It's basically, it's like a farmer's almanac, really. You know, that's what a farmer's almanac does. It's you know, a compilation of climatological data that gives you estimates about when at different times of the year, things like planting. I'm not a farmer, but it's my understanding of the way the farmer's almanac was developed. So this is kind of a graphical version of that. The problem is, though, if this is based on a certain baseline, what's going to happen when, you know, everything is 5 or 6 degrees warmer? Okay, the last 15 years, okay, are the warmest in recorded history, and most of that heat is going into the oceans. The seawater or water in general is much more efficient at absorbing and keeping heat than terrain, so about 90% of that heat's been absorbed by the oceans, and to the tune of, again, a global average, there's been a 0.8 degrees Celsius increase in the average sea surface temperature globally over the last 100 years. And that doesn't sound like much, but in terms of energy, it's tremendous. It's just an unbelievable, like, you know, when you read the actual units, you know, they have units that are like, you know, atomic bombs per second in terms of the amount of energy that's been absorbed by the oceans over this interval. So what that means in terms of weather, okay, the oceans are warmer, okay, so the oceans are warmer, so that means just like when you heat water up on the stove, the more you heat up, the more it wants to evaporate. Warmer water evaporates more quickly, more substantially, so there's more water vapor in the atmosphere to make clouds and weather. Water vapor effectively carries energy up into the atmosphere. Water vapor goes up into the atmosphere, and when it condenses into clouds, it releases heat, okay, which is a mechanism that's really a mechanism that storms use to develop, okay? So the more water vapor you have, this is actually an acronym I just ran across, they call it WAP, okay? It's water available for precipitation, okay? So there's about 6% more water available to make clouds and precipitation than there was 100 years ago. If you do the math, if you're interested in this, there's a fantastic scientific team, I'm sure one of many, but at MIT, led by a guy named Kerry Emanuel, Professor Kerry Emanuel, and they've done a lot of the math on this, right? But the equations sort of reveal that this amounts to about a 25 25 knot increase in the theoretical potential energy of things like tropical cyclones, right? So there's, storms now have the potential to be about 25 knots. So that's, somewhere between 20 and 25% stronger, right? Potential strength of tropical cyclones than a century ago. Another important point, kind of looking outside of the tropics, is the poles are warming faster, right? So the old climate boundaries are less stable. So let's kind of look at what this means. 2020, okay, a record hurricane season, 30 named storms, okay? Probably many of you were, I'm sure many of you are aware of this already, right? That was kind of one for the ages, except it was really just one of many. If you look at record hurricane seasons, right, 2020, okay, these are in the order. These are the last 9 record tropical cyclone seasons in the North Atlantic. Here's 2020, okay, 2005. 2020 displaced 2005 as a record season, and then there was 2021, 1995, 2010, 2011, 2012. So this is 9 seasons, right, and of the 9 record Atlantic hurricane years, 7 of them have been since 2000. 7 of them have essentially been in the last 3 decades. Okay, so a clustering of record hurricane years over the last 20 or 30 years. Okay, this is just a couple of years ago. Sanibel, tremendous amount of destruction, right? Gulf Coast of Florida. Sort of more data, right? This is so we're talking about category 4 and 5 hurricanes. So these are hurricanes with wind strengths of above 135 knots, and we can see just the 20-year average occurrence of these since this 2000 here, 2020. So over 2 decades, the average occurrence per year, right, has just about doubled. Okay, the 20-year average has just about doubled. An average of 1 per year over 20 years to 2. Okay. And we're just talking about individual storms of this strength. So all the arrows sort of pointing in the wrong direction. Okay, so this is how we are in 2024, and I don't know, like if you've been reading the news, they're talking a lot about this year was going to be, a record hurricane year. The tropics were very, very warm, the oceans were warm, everything was warm, and things were kind of set up for a big year. And so, this was a couple of weeks ago, right? This is from the Washington Post. What happened to the predictions of the historic hurricane season, right? And we just had, August was beautiful, right? And we were all sort of waiting, but not much happened. Atlantic Ocean just made history for the longest late summer stretch without a tropical cyclone. Meteorologists are concerned that delicate public trust is at risk. So it kind of gives you this what meteorologists really worry about at night. It's not weather, right? It's, being taken seriously. Okay. Okay, this is the next day. Okay, so September 10th. Okay, so this is a graphic from the National Hurricane Center. They publish these every day. This is their 7-day outlook. Red is bad, right, as it is in most cases. Okay, what do we got? So not a week later, 2 weeks later, but a day later, suddenly, okay, in the western Gulf of Mexico, we have a not quite a hurricane, a tropical cyclone. It was a tropical storm named Francine in 2 areas that are, when you're at this red area, means over the next 7 days, there's better than a 60% chance of a tropical cyclone developing. So significant, right? Activity, things starting to pick up again. Okay, so even though August was fairly quiet, there's still a lot of energy there. Okay, and this is the weather map that we looked at earlier, a little while ago, right? And we can kind of see, right, if we look down in the tropics, right, we can actually see, right, well, we have, T tropical. It's not quite a storm, tropical depression, so not super strong, right? But there's a tropical cyclone here. There's not fully tropical, right? But here's a storm that has the potential to develop into a tropical cyclone. And then there's this, I don't know if anybody's just been over the last couple of days, right? North Carolina just got clobbered. They got like 2 feet of rain in half a day, okay? And this was, again, same sort of thing. It was tropical energy, so a very warm, moist atmosphere, and they just got a ton of rain. The wind didn't make it up to hurricane strength, but it was a circulating, very similar, like a hurricane-like storm. Oftentimes, really, with tropical storms in particular, the wind is dangerous, but in a lot of cases, the water is the most dangerous part. You deal with, flooding and things like that, and the water does, in terms of loss of life and damage to property, the water is really what does the most damage. So just sort of looking out of the tropics. The other thing that as the poles get warmer, okay, compared to the rest of the Earth, these boundaries, the boundaries between major air masses, become less stable. So things like the jet stream, which is usually a fairly strong, steady west-east flow, the jet stream gets sort of jiggly. It slows down and tends to get, becomes more sluggish and more erratic. Okay, and so what that does is, again, you sort of get these. That tends to lead to more rapid swings in weather, and sort of sudden weather events. And we think about, like, somebody asked me last winter. We had this tremendous series of storms, right? I'll look at those first. Okay, last winter, we had in January, right, we had those two coastal storms right in a row, okay, and somebody said, well, does it have to do with climate change? And well, yeah, I don't know, I'm not a climate scientist, but what was going on there right at that point, we had this really abrupt, this is the jet stream, okay, and it was pushing way to the south. It was, dipping way down over the continental U.S., and it stayed like that for several days, and as it did, all this cold air that was being kind of pushed down out of the Arctic was meeting up with a lot of warm air. It was being pulled up out of the tropics. I don't really have time to talk about El Nino, but there was a lot of tropical moisture in the North Atlantic last winter as a result of El Nino, and it ran into this very cold polar air. And this was air that was actually very cold over the North American continent, but the other side of the planet was very warm. Asia had record warm winter last year, and so all that warm air was displacing the jet stream. So this is the kind of stuff that can happen as the sort of standard boundaries, the climatological boundaries between different regions get disrupted. They become less abrupt as the poles get warmer. Okay. Again, looking at just recent history, right? We just had something in Europe. I mean, we mostly read about this or heard about it on the news, right? There was a fairly catastrophic weather event in Central Europe. Similar kind of circumstance. There was a very large intrusion of cold air into Western Europe, and that bumped into, this is the Mediterranean here, a lot of very warm, humid, the peak of summer. And that temperature difference, right, led to the development of some very powerful storms right along that boundary. And again, not the kind of pattern that you expect to see the jet stream have, okay, but the poles themselves are warmer, and so the jet stream isn't as subtle. So these sort of, really rapid swings in temperature and really powerful weather development at the surface, again, is something, they're still doing the math, right, but, it's pretty clear that seems to be connected, again, to a general warming across the atmosphere. So these are so this is last winter, right? These are the two. Is anybody who was here for these? Yeah, right? So this is not the same weather map, okay? This was January, I can believe I finally, after I built my house up in Surrey about 30 years ago, and last summer I put in a generator. And boy, was I glad. Yeah, so this is not the same storm. This is two storms back to back, okay? January 10th and January 13th, and you can see, right, the isobars, right, if this was a hill, it would be steep, right, it would be a big hole. Okay, so these are two just incredibly intense. These are really hurricane strength, low pressure systems happening right after one another, and they're both the result of, just this large area of cold air that's pushing down out of the Arctic, carried by the jet stream. Okay, I'll just whiz through the last, a couple more slides here. You can blow a whistle, I've been talking enough, but just thinking about other impacts in terms of navigation. A tremendous amount of cargo gets carried at sea. A lot of cargo gets carried on rivers. Not a lot of people realize this, at least at first glance, right? But the Mississippi River system is something similar in Europe. Tremendous inland river system, carries a huge amount of cargo by barge. And they need water, right? So as rain patterns get interrupted, the rain is still falling, but it's falling in different places. So both the Mississippi and the European Inland River System experienced drought last summer, in the summer of 2022, and then again this year, with major interruptions in barge traffic. So just the inability to bring things, most of it is things like grain and things like that, agricultural products. River traffic on the Mississippi was heavily interrupted. Probably not, I mean, I don't know how many people are aware of this, but this is the Panama Canal, okay, and the Panama Canal to operate actually also relies very heavily on rain, and Panama is sitting right in the tropics, so it's, you know, historically a rainy part of the world, but Panama has had a couple of dry years, and as a result of that, basically to run the Panama Canal, they let water out of this big lake that's right in the center of the Panamanian Isthmus, Gatun Lake. That lake has to be full of water, right? Or eventually they can't run the locks. They can't drain the lake into the locks to lift ships up and lower them down. Things have gotten a little bit better, right? But the sort of historical rain patterns, nobody had ever seen anything like it. But you know, last year, the summer of 2023, there were some restrictions on, you know, the number of ships that could transit, and also the draft, essentially the amount of cargo they could carry, because they just didn't have adequate water to run the canal at its usual pace. Okay, and then finally, last of all, right, another, you know, lecture in and of itself, but there's all these places you didn't used to be able to go, right? This is the Arctic Ocean. Okay, so here we have the Northwest Passage, right, the storied Northwest Passage, sort of holy grail, right, of exploration, and then we have the so-called Northeast Passage, or the Northern Sea Route, and then the route right across the pole. These are all places where you really, you know, historically, right, you just couldn't go. You can book a cruise through the Northwest Passage now, okay, and with, you know, Viking cruise lines and things like that. So there's commercial ship traffic going through the Northwest Passage, as is through the Northern Sea Route, right? And actually, I was just reading last week or the week before, it was the first time two full-size, two Panamax container ships passed one another in the Northeast Passage just a couple weeks ago for the first time. So this is turning into an area of, you know, commercial navigation. You know, a couple challenges there. You know, the charts aren't so good, okay? And it's also the issues of ownership and, you know, territorial ownership. And, you know, it's like, think about the Northwest Passage through Canada. You know, is this more like the English Channel, or is it more like the Panama Canal, right? And if you ask the Canadians, they say, well, the Panama Canal, right? But, you know, if you ask, well, say the Russians or the Americans, right, the other Americans, they say, oh, it's, you know, an international passage, right? So there's all these, as well as the navigational issues, there's some territorial issues that, you know, are being raised also, right? You know, how is navigation regulated and controlled and things like that. So, you know, and the Russians have about 50 full-size icebreakers. Some of them are nuclear powered. We have 2 right now, so something to think about. So I will wrap up there. Happy to take any questions, or thank you for your patience.